Welcome back. I hope you're ready to get back into things. Don't worry, we'll review a little bit at the beginning. We're on to Unit 6, and just so you have a sense of scale, this course is divided into 9 units, and the last two, Units 8 and 9, are by far the shortest of all the units. So we are well over halfway through all the material for the course, and I feel like we're in a pretty good spot for the time of year that it is to be starting Unit 6. So, in Unit 5, the one we just did, we talked about a lot of different things, but specifically, one of those things, for categorical random variables, then we can talk about the sampling distribution for a sample proportion. So this is the idea that in a large population, we could take all the possible samples of a given sample size and calculate the sample proportion of whatever the random variable is for each of those many samples, and then look at the distribution of those sample proportions, of those p-hats. And we said that if we meet certain conditions, we can say that sampling distribution has this shape. It's normal, so it's nice, unimodal, and symmetric, and we also know the mean of that sampling distribution is the population proportion, and the standard deviation is the square root of p times 1 minus p over n. Right? And I said that we would be using the ideas of these sampling distributions going forward. Well, this is the forward that we're talking about. So let's get into an example here where we might be using some of these ideas. In December of a recent year, Gallup conducted telephone interviews with 1,049 randomly selected U.S. adults, and 62% of them, which equates out to about 650 of them, had taken a vacation that year. And just before we talk about anything any further, this is not talking about the year 2020. Obviously. I feel like if they did that, that percentage would be a little lower. But that is our example. And let's say what we want to know is, what is the true proportion of all U.S. adults who took a vacation that year? It would be good to know what the true proportion is for the entire population, mainly because if we want to use what we know about sampling distributions, take a look at the parameters of that sampling distribution. P and the square root of p times 1 minus p over n, we need to know what p is in order to determine that sampling distribution. What is p? That's what we want to know. Is there anything in the problem that would suggest that we know what p is? P is the proportion of U.S. adults in the entire country that went on a vacation that year. I don't think we're given that in the problem. In fact, the only numbers that we're given are 1,049, which is the sample size, that's n, 62%, but that's the proportion in the sample. So this is 62% of the 1,049 people. So this is actually p hat. And then the 650 is just the number that you divide by 1,049 to get your p hat. None of those are p. Is that a problem? So what is p, the true proportion in the population? Can we just say, hey, let's just use p hat for that. Let's just call the proportion in the population equal to 0.62. That's what it is in the sample. Well, no. Just because we took a sample of 1,049 individuals in the population and calculated the sample proportion, does that mean that it is exactly that way in the entire population? Of course not. If we took a different sample of 1,049 U.S. adults, we would probably get a sample proportion that was a little different than 62%. Maybe it would be 48%. Maybe it would be 81%. It probably wouldn't be 62%. So no, we can't just say that because each sample would have its own sample proportion, and that's probably not the proportion in the population. So it turns out we can't use p hat in place of p here. We can't just assume we know something about the population if all we did was take a sample. So how the heck are we supposed to find p? we need it to calculate these parameters and utilize our sampling distribution. How can we use what we know about our sample to tell us something about the population? Well, there's good news and bad news. The bad news is, without sampling every single adult in the United States, we will never know what this is. And that's actually realistic. In most things that we want to know about a population, we don't already have the parameter at hand. Everything we talked about in Unit 5 when we calculated the parameters for this sampling distribution, we assumed we knew what P was, the population proportion. But in the real world, especially for variables involving large populations, we don't know what P is. We don't know what mu, the population mean, is. So we can't use this. That's pretty bad news, because we just took an entire unit talking about them. The good news is, even though we'll never know for sure what this true proportion in the population is, we can use the information we know from our sample to be able to put an interval within which we can be fairly confident that P is in that interval. So we're not going to be able to pin down and say P is this number, because all we did was take a sample. But we are going to be able to say, based on the sample we took, we can be fairly confident that P is somewhere in this range, somewhere in this interval of values. And that's a lot of what the next few lectures is going to be about. Taking information from a sample and being able to use that to say something about the population. Here's what we're getting at. For a single categorical variable, such as the proportion of US adults that went on vacation in a recent year, we can construct what's called a one-sample Z interval. And that is going to allow us to estimate the population proportion P. Okay. A one-sample Z interval, it's going to be an interval of values within which we're fairly confident that P is inside. And we'll talk more about that later. And the one sample part is because we have one sample at a time here. Just like when we talked about sampling distributions, where we could take a sampling distribution for a single sample or for two samples, we're going to be doing the same thing with these intervals. There will be one sample ones and two sample ones. The Z part of Z interval suggests that we're going to be using the normal distribution just like we did in the past. There will be intervals we talk about that use a different distribution, and it will be a different type of interval. But this is, the one sample Z interval is the first of several what we call confidence intervals that we'll construct. And the purpose of these confidence intervals is to estimate a range for a population parameter from sample data only. In the past, in all of the first 5 units, if we calculated probabilities or used models, we assumed we already knew the population parameters. That's how we came up with those models. We are now taking away that artificial knowledge that we probably wouldn't have in the real world. We don't know what the true proportion is in the population here. So we're going to use this idea of a confidence interval to be able to say something about a population using models without knowing anything about the population ahead of time. So we will get into the mechanics of how to construct this one sample Z interval. Maybe in this video, probably 1 or 2 after this. I want to set up everything we need to know before we construct the interval because, again, I want to make the point. Being able to calculate things in this class, sure, that's great, that's important. What's really important to me is that you understand why you're doing these calculations and what they mean. So this is like a whole new way of seeing statistics. In the past, we just calculated things assuming we knew things about the population. This is a seismic shift away from that. We don't know anything about this population. All we know is what we have from our sample. So what we're going to be doing is we're going to, for these one sample z intervals, we are going to have a p hat that we calculate from a sample, like this 0.62, and we'll have n, the sample size. Here it's 1049. From just these two sample statistics, we're going to be able to say something about the population. We're not going to be able to pin it down and say this is the proportion of US adults that went on vacation that year, but we're going to be able to say something like we are C% confident that P is within an interval between two values. This is going to be our goal. This is what we want to be able to say, and being able to calculate a one sample z interval will be able to help us say this. And I want you to understand how powerful that is. Based on just a sample, knowing how big that sample is and what the proportion in the sample is, we can say something about the population. That's really powerful. And that's what the rest of the units in this course are going to be doing. We're going to try and say stuff about the population given a sample under different conditions. One sample or two samples, proportions or means. We'll even go back to when we talked about linear regression and do it with the slopes of the regression lines. We can do all this with that as well. So, but for right now, we're only talking about one sample proportions, and our goal is to be able to calculate this interval. But in order to do that, we need to go back. So just in case what I've said so far isn't particularly clear, it's a fairly radical idea that we can say something about an entire population based on just taking a sample. How is it that we can do that? The sample may not reflect the population very much. Maybe it's a weird sample. But we already know, based on the sampling distributions that we've talked about, specifically for this example, the sampling distribution of p hat, it tells us how samples of a given size vary within a population. We know that the typical sample proportion in this population is going to be centered around p. And that if you go more than 2 or 3 standard deviations on each side from p, that's not going to be very likely to happen. That's very powerful. We actually do know something about the population based on a sample because we know how these samples behave. We know how these p hats are distributed. They have a normal distribution with this mean and this standard deviation. So that is going to be the key to allow us to do this. We know how samples in a population vary, even though we only took one sample. We know how those samples are distributed. So, to calculate these intervals, which is going to be our goal, we want to be able to use the sampling distribution of p hat, this one, that we talked about in the last unit. But to use the model that we're familiar with, where that sampling distribution is normal with this mean and this standard deviation, we have to check the conditions that we checked before. Do we remember what those conditions are? Well, there were 3 conditions total that satisfy 2 different assumptions we're making. So in order to say that the sampling distribution of p hat follows this distribution, we need individuals to be independent of each other, and we really need to check 2 conditions to make sure that this assumption is appropriate. We need the sample to be randomly generated in some way. Randomness needs to be involved. It needs to be a random sample. It needs to be a random sample, or if you're talking about an experiment, if you want to calculate this one sample z interval for an experiment, the treatments need to be randomly assigned to the individuals. Remember, for an experiment, a random sample is not necessary. The randomness in that sense comes from how the treatments are assigned to the experimental units. We also need to make sure that we are sampling either with replacement, which would be fantastic, although not really useful. We don't want to sample with replacement here because we don't want to get the same adult twice. We're usually going to be sampling without replacement. So in order to be able to assume independence, we need to be sampling a fairly small fraction of the population. This is the 10% condition. If you're sampling a larger proportion of the population than 10%, then every time you're sampling someone, you're actually changing the probability that they go on vacation of the population every time you pick one. At that point, the individuals aren't independent anymore. If you're sampling less than 10% of the population, you can assume that those probabilities aren't changing very much with each individual you sample, and you can assume independence of those individuals. Now, we need that, and in order to be able to say that the sampling distribution follows an approximately normal distribution, we need to check the success-failure condition. You remember the success-failure condition, right? N times p is at least 10, n times 1 minus p is at least 10. So, just like in the last unit, if you want to be able to say that the sampling distribution of p hat is approximately normal in shape, this condition has to be met. Is there a problem here? There is. Are we going to be able to check this condition? If I asked you to check the success-failure condition right now for this example, how would you do that? We don't know what p is. Remember? We don't know. That's what we're trying to find out. That's the whole point of this. We don't know what p is, but we need p to check this condition, so what are we supposed to do? Well, it turns out our best estimate of what p is p hat. So this might seem like cheating, that we're just plugging in p hat because we don't know p. And to a certain extent, yes, we are losing some specificity there. It is possible that p hat and p are wildly different, and maybe by using p hat here, it could end up that this condition's met, whereas if we knew what p is, maybe it wouldn't be met. But again, if we can't substitute in p hat here, there's nothing we can do. We're not going to be able to use a sampling distribution model for p hat. We're not going to be able to calculate our interval. We have to be able to do something. And we already know that p hat, the mean of the distribution of p hat, is p. It's an unbiased estimator. So it's actually not a bad fallback plan for not knowing what p is here to check this condition. Just plug in p hat, and that's actually not a bad backup plan. So to recap, the conditions that you need to check to be able to use the sampling distribution model for p hat are the things in these clouds. We've got our two conditions that allow us to assume that individuals are independent, and we have our success-failure condition that allows us to say that the sampling distribution is approximately normal. So let's check these conditions really quick for the example that we've started here. Do we have a random sample or random assignment of treatments? Well, first of all, this is a sample, not an experiment. So was the sample randomly determined? Yes, it says right here, the US adults were randomly selected. Good. Are we sampling less than 10% of the population? Well, yes. There are definitely more than 10 times 1,049 US adults. So that condition is also met. Is the success-failure condition met? Well, do we know what n and p hat are in our example? N is the sample size, that's 1,049. P hat is the sample proportion. That's our 62%, or 0.62. So if we take n times p hat, that's 1,049 times 0.62. And that is going to be, what is that equal to? It's about 650, which is what we would expect because that's how we got this number. That's greater than 10. And if we take n times 1 minus p hat, that's 1,049 times, that's going to be 0.38. And that'll give us about 399, which is also bigger than 10. So the success-failure condition is met. These two conditions are also met. That is going to allow us to say, hey, we can use the sampling distribution model for p hat, and we know it's normal in shape. So we said that that sampling distribution was p hat is approximately normal with a mean of p. I'm taking that from here and here. It's the same thing. Sampling distribution of p hat and a standard deviation of p times 1 minus p over n. Any problems with that sampling distribution? If I told you to calculate what the mean and standard deviation of that distribution were, could you do it? I feel like a broken record. We don't know what p is. But look how p is involved in both of these parameters. We can't calculate those. It's kind of like the problem that we had here. We couldn't check this condition because it had p in it. We don't know what p is. So what can we do? Let's do the same thing we did when we checked the success failure condition. Everywhere we see a p in these parameters, we're just going to substitute in p hat. So back in Unit 5, when we lived in happy world where we knew what p was, when p was known, the mean of this sampling distribution was p, and the standard deviation of the sampling distribution was the square root of p times 1 minus p over n. If we don't know what p is, which is more realistic, and that's the assumption we're going to be working with going forward, the mean of that sampling distribution is now p hat. Okay, we don't know what p is. P hat's our best estimate, so we're going to use that for the mean of the sampling distribution instead. The standard deviation also gets those p hats plugged in, but we don't call this the standard deviation of the sampling distribution anymore. The standard deviation needs this to be p. If we're going to plug in p hats, we can't even call it the standard deviation anymore. The standard deviation of sampling distributions are very uppity, they're very stuffy. They're like, if you don't use p, you can't call us a standard deviation. So we call it the standard error instead. So in this new universe where we don't know what the value of the population parameter is, in this case, since we're talking about proportions, we don't know p, the sampling distribution, we no longer can calculate the standard deviation. This is just as unknowable as p is, but we can calculate the standard error, which has the p hats filled in instead. It's important to know, even though we're changing p to p hat here, we still call this the mean of the sampling distribution. It's not like we changed the name to like standard mean or something weird like that. It's still the mean, and that's because p hat is an unbiased estimator of p. And not to get too far into the weeds, but the standard error is not an unbiased estimator for the standard deviation, so that's why we have to change the name. It can be a little confusing, especially when you're first starting with standard errors, to know when you're using standard error versus when you're using standard deviation, because you're going to be using the standard error in all the same contexts that you used to use standard deviation for these sampling distributions. The key thing to know is it's a standard error if you're using the sample statistic, in this case p hat, instead of p. Okay, and don't worry, we're going to go through the calculations of this one sample z interval. You're going to see how the standard error comes into play and why it's not the standard deviation. I'm going to make that as clear as I can. And in future videos, we're going to look at different intervals for different types of populations. And we'll see how they all work together to tell us similar things. I think that's enough for this video. We've changed the game a little bit. The main idea here is we still want to use the sampling distribution of a sample proportion, just like we did in the past, but we don't know p, and that complicates things. It means we have to substitute in p hat, where we see p for the sampling distribution. And what it is we're trying to do with all of this is to be able to say something about a population based on just a sample. And the first way we're going to learn how to do that is by calculating an interval by which we can say, hey, we are fairly confident that the parameter we're trying to find is somewhere in this range. You're going to find that saying something like this is a lot more interesting than saying our best guess for P is whatever P hat is. That's true, but it's not super exciting, and you can't be very confident that P is P hat. But if you can say something like this, that is much more powerful. And we'll talk about how that is calculated starting in the next video. And we'll see you there.